Alright, friends and neighbors, welcome back to another networking video. Today we are talking about broadcasting. So without further ado, let's talk broadcast. Now to get started, I would like to talk about broadcast addressing as opposed to a broadcast media. So first we're going to look at this switched topology. So we can see we've got a couple of switches, right? And then we've got a couple of PCs, and all three of them are on the 10 net. And what we're going to do is take a look at how switches behave in the presence of unicast and broadcast addressing. Now, broadcast addressing is going to have all F's in the destination. So that's hexadecimal, 6 bytes of all F's. And first up, we're going to take a look at the Arp table, because that's really at the heart of this particular evolution. And so we see that there are no Arp table entries. So PC1 here doesn't understand where everybody is. So if I start and I just ping, what I'm going to do is ping between PC1 and PC2. So pretty straightforward operation, right? And we can see that I'm queuing up a couple of messages here. So it turns out, and let's get these on the screen for us. We can see that it's an Icmp and an Arp. Well, we want to send an Icmp. That's what ping does, an Icmp echo request. But to do that, first we need to build an Ethernet frame, and so we need to discover the MAC address. And for that, we need the address resolution protocol. So we take a look at this. We can see that PC1 is trying to discover the MAC address for PC2. That's the whole point. So we can build that Ethernet frame. So this is a broadcast frame. Right? So this is not really about ARP, but this is really about what happens when we send broadcast messages. So what we're going to see is that switch 0 gets this broadcast frame. Broadcast destination MAC address, source is a unicast, and it's going to blast this out everywhere except the port that it came in on. The other switch over here will forward the same messages, and the switch 2 will also send it down to PC3. And that's by design. We want switches to forward broadcast addresses everywhere because we're trying to find somebody. So let's step through this a little bit. We can see that this broadcast frame reaches switch 0, goes down to PC2, but also over to switch 1, over to switch 2. Now this message coming back is actually the answer from PC2. So this is a unicast message. We know that because the destination MAC address is unicast, the source MAC address as always is unicast. But what PC2 has done is filled in its MAC address and says, well, you were looking for my MAC address, here it is. But what we're really interested in is the behavior of the broadcast frames. So switch 1 blasted it out everywhere, switch 2 blasted it out everywhere. So PC3 is going to get this broadcast message even though it's not involved in the conversation. Okay. So the broadcast frame went everywhere by design. That's what switches are supposed to do. Now the next question is, what do they do with the unicast traffic after that? And the answer is that switches only forward the unicast traffic to the endpoints that are involved in the discussion, the endpoints that need to get it, the endpoint that has that destination MAC address, at least once they've learned where everybody is. So the thing that we're going to look at now is this Icmp echo request that's going out. Now notice it goes out here. Let's take a quick look at it. This particular message is unicast at layer 2. And so we see that we've got 2 unicast addresses, but of course the big one is going to be the destination MAC address. Okay, so it hits switch 0. What does switch 0 do? Oh, it just sent it down here to PC2. Did not send it over here to switch 1. And that's because switches care where traffic goes. Well, what helps them with that? So we don't need our real-time or our simulation anymore. What helps them with that? And the answer is the source address table or the MAC address table. And if we take a look here, what the switches learned is where the destination MAC addresses are. So when PC1 and PC2 are having a conversation, after the switches learned where they are, it only sends the unicast traffic where it needs to go. broadcast traffic gets blasted everywhere. So switches are very, very concerned with where MAC addresses are and only forward broadcast frames, that is, frames with an address of all Fs in the destination to everybody. What do other kinds of devices do? So here are the same set of nodes, but now we're connecting them via hubs. Now the fundamental difference here is that hubs are essentially multi-port repeaters. All that they care about is cleaning up the electrical signal as they forward things on. So that means that their behavior in the presence of traffic is going to be different than switches. So this is what we call a broadcast media. Now we can see that we've got some stuff queued up here, so it'll be interesting to see what that is. But this is, I'll just put this as an aside here. We can see that this particular node is ARPing for itself. That's a gratuitous ARP, and that is how operating systems verify that there's nobody out there with the same IP address. Okay, so let's go to the same transmission. I'm going to do the exact same thing. Let's check the Arp table. So again, PC1 has no Arp table entries, and so I'm going to ping PC2. Alright, so we got things queued up here. Same exact thing, right? We've got Arp and Icmp, and this Arp request, now this is a broadcast frame because it's got all Fs in the destination, but that's not really the issue here. We're going to see what it does with unicast traffic. So the hub sends the broadcast frame out everywhere. This is the same thing that the switch did. Now we see that the Arp request is coming back. The Arp request is, oops, I grabbed the wrong one, from PC2. So here the Arp response is unicast, and we'll see that the hub blasts it out everywhere, but it'll be a little more obvious when we do the ICMP. But we can see that this message coming right over here is unicast. The hub was not supposed to send it out to everybody. Well, it is because it's a hub, but it's blasting out this unicast traffic everywhere. So we'll just step through to get to the next ICMP. Alright, here we go. Right now, alright, so we got this pretty color here, this violet or whatever that is. So it goes down to the hub. Now, what is this? This is a unicast frame because it has a unicast MAC address in the destination. So you would think, based on what we saw with switches, that this hub would send it right down here to PC2 and only to PC2. But it's a hub. It says, I don't care about MAC addresses. I don't have a table like that. So I'm going to blast this out everywhere. And so PC3, way over here on the other side, sees the conversation that PC1 and PC2 are having. Okay, so this right here is a demonstration on why we don't use hubs in networks today. Not only do they blast things out everywhere, but this also creates the potential for collisions. This entire topology would be what we call a collision domain. Everybody in here, if two frames collided, meaning that two nodes transmitted at the same time, that spike in voltage or power would be seen by everybody. So this entire thing would be called the collision domain. On a switch topology, the whole thing would be a broadcast domain. So hubs are very fast, but that doesn't help us when we have collisions, so we're destroying transmissions. In addition, this entire topology is what we call half duplex. So only one node can talk at a particular time. So here we are back with our switches, and again, this is called a broadcast domain. Why? Because this is the region over which a broadcast frame will be broadcast. Now the boundary for a collision domain is a switch. Switches don't forward collisions. The boundary for a broadcast domain is a router, because routers will receive and open broadcast frames, but they won't forward them. Now the funny thing about a topology like this is that every once in a while we do want to see. Let's say that this is a monitor node and we want to see this conversation. Well, how would we do that? Well, in this case, we might set up monitor ports or do what we call mirroring or spanning. And that's where we copy traffic from a particular port to another node so that we can see what's going on. So that's actually a feature that we have on switches that we like to use without having to install hubs everywhere. So that was a little detail on broadcasting. So we talked about the difference between a broadcast media, which is what we have when we have hubs in the topology and we have all of the problems, speed, but we wind up with collisions and it's only half duplex, so we're limited in capacity. As opposed to broadcast addressing, which is all Fs in the destination MAC address. So really the two topologies was the difference between switches and hubs. And we also talked briefly about what monitoring. Monitoring is that feature that switches give us so that we can do the same thing that a hub does, right? We can copy traffic or we can see a conversation that's happening elsewhere in the topology without having to install hubs. Now the funny thing is that everybody does wireless these days. We like wireless laptops, we like even adapters for desktops, and of course cell phones connected to our data networks. The funny thing is that wireless, in a way, is a step backwards because that's a broadcast media. Everybody hears what everybody else is doing, which is why mind your security when you're on a wireless network. Well, that's it for this particular video. Like and subscribe if I helped, and may those packets always reach their destinations, whether or not you're doing a shared media, broadcast media versus broadcast addressing.